Wrap up of mass of a planar lamina. What the heck is a planar lamina? It's a thin film in 2 dimensions. So we're just finding the mass of the planar lamina if the density is variable. The density is constant, just multiply whatever that constant is times the area of your lamina. But if the density is variable, then you'll want to put the function for the density. We're calling it rho. Rho is a Greek letter. You may see this as F instead, F or rho, depends on the problem or the textbook. It's just a function. You stick that in the integrand, and then you set up the double integral where the region of integration is your lamina. Okay, so we already did one example where the lamina was this triangular region, and we had a variable density function given to us there, and we got the mass. Fine. Now, the next problem is a little bit more tricky because they're not giving you the density function outright. You have to use a little bit of knowledge. So we're going to find the mass of a lamina corresponding to the first quadrant portion of a circle of, radius 2 centered at the origin there, x squared plus y squared equals 4. So there's our region of integration. There's the region R. And the density at any point xy, here's a point xy in the region, it's proportional to the distance between that point and the origin. Well, here's the origin. So here, if we do the distance, remember distance, you know this from an algebra class, is the square root of the sum of the differences, the square of the differences between the x and y coordinates. So this distance formula here is just going to give us that. So that is the density function. So rho of xy, this function of two variables, this is the density function right here. Yay, we have it now. We're ready to go. Okay, so what's the mass? The mass is equal to the double integral over the region R. Oh, I forgot to tell you something. It's proportional, so we need to put a constant of proportionality in there. Yeah, sorry. K is a constant of proportionality because they just told us that the density function is proportional to the distance. So there may be some constant thrown in there that we better account for. And that constant, I'm just going to pull it out in front of the double integral. And then we've got this distance formula and then dA, the area element. Now, folks, what do you think I'm going to do? Do you think I'm going to stay in the rectangular coordinates, or should I convert to polar coordinates?
Polar.
Polar is correct. Why?
Because the area is inside of a quarter circle, and x squared plus y squared could equal r squared.
Two good reasons. One, the big reason is your region of integration is a circle or a portion of the circle. And also you've got that x squared plus y squared thing in there, and that's no fun to try to integrate with respect to y or x or anything like that, unless you want to do trig sub. Who knows? Yeah. Ooh, I want to do trig sub, said no one ever. So yeah, we're converting to polar. So this is going to be the square root of r squared, which is just going to, simplify to r. The area element for polar is what?
R dr d.
R dr or
dr d theta. And then the region, this region here has r blossoming between 0 and 2. Remember r always starts here at the pole and it kind of works its way out. And then theta is only going between 0 and pi halves since it's in that first quadrant. So we set up these little integrals, and then square root of r squared is just r, and then multiply your r's together to get a single power of r, and now you can integrate, and you're like, okay, r cubed over 3, fine, going from 0 to 2, and 2 cubed over 3 is 8/3, so you'll just pull that out, and now you're just integrating 1 with respect to theta, and that's just theta. 0 to pi halves. Oh, I keep forgetting my k. That doesn't go away. Pardon me. just trying to go too fast here. K is still there. And your final answer, you got the K, the 8/3 times the pi halves. And I'm going to reduce this to lowest terms, and I get 4 pi K thirds. And there is the mass of this planar lamina. Luke, I don't know how you can see the share screen. Maybe it's because you're on the move or mobile. I'm sharing my screen. Does anybody have a fix for Luke there? Not sure. Not sure how to help you there, Luke. Sorry. Sorry. You'll have to watch the video recording. That's always a bummer. You know, technology. Yeah, try restarting. Yeah, Jake, that's always the go-to, right? Hey, reboot. Let's do area of a surface. So brand new topic. In Briggs, we are officially jumping over to a section in chapter 17, 17.6. And I just want to let you know that not all books do this. Some other books, the books that I originally taught this course out of, had this surface area concept, which I'm about to do, in the double integral chapter. And that's why I still like to teach it there, because I think it's apropos. In other words, it's another wonderful, relevant application to use a double integral. So what do we know so far? Let's do a quick summary of what we know how to do with double integrals. So one thing you guys should know how to do with a double integral is find the area of some region R. And that's if the integrand is a 1. Then that double integral is being used to find the area of some region. Another thing you can use a double integral for is volume of a solid where the capping surface is f of xy. And so the volume would be the double integral over the region R, which the region R would be the projection of the function onto the xy plane. And you'd put your capping surface there in the integrand. So I'll just put that R is equal to a projection of the function onto the xy plane. Now, there's another way you could do volume if you have a ceiling and a floor function, and we saw an example of that last time, where you would have your ceiling and then minus the floor. And then your region would be the projection of the solid again onto the xy plane. Okay, so and then finally, the mass of a planar lamina we just did, where the density is given by some function rho of xy. And so your mass, I'm running out of room here, is your double integral over the region rho of xy. So these are the 3 things now that you know that a double integral can be used for. Congratulations. Let's give you a 4th thing that a double integral can be used for, and it's going to be surface area. So let's look at the diagram right here. You've got a capping surface that's hovering above the xy plane, and so the region R is the projection of that solid, or the shadow of the solid, onto the xy plane, which is given by R. And we don't want to find the volume now. We actually just want to find the surface area of this capping surface. So if we had to lay some wrapping paper just to cover up that capping surface only, you know, how much square footage of wrapping paper would we need? That's surface area, not volume, surface area. So the surface area is a little tricky because, you know, because this surface is so curvy, how the heck are you going to get that surface area? I don't know. I don't know how to find the surface area. So the strategy is to take a little tiny patch of surface area, tiny patch corresponding to one of these rectangles down here in this partition that they performed on the region. So hovering right above that little ith rectangle, if you will, is a little curvy patch of surface area. But the surface area you can see there is kind of curvy. They're calling that little surface area patch delta S sub I. So that's too hard. So what we're going to try instead is if we take that point there, that ith point on the surface, and instead we do the tangent plane to that point. You guys know how to find tangent planes to a point on a surface because we did that last chapter, right? So we're going to do a little patch of tangent plane that they're calling delta t. So this is a little patch of tangent plane. So the idea, folks, since we don't know how to find the surface area because it's way too curvy, we're going to look at a flat, tiny patch of tangent plane instead. And then the idea is, of course, is to basically paper this entire surface with little flat tangent planes everywhere. Oh, it's kind of hard to draw these little flat tangent planes. And then add up all the little teeny tiny patches of flat tangent plane. And of course, we're going to form a Riemann sum. And then we'll take a limit. You know, that's how we're going to roll. So consider the surface defined over the region R, assume that R is closed, this is a region R down here, and bounded, and F has continuous first partials on that region. And then you're going to construct the inner partition of n rectangles, okay? Find the area of the ith rectangle, delta A sub I, which is just change of delta X, delta Y, that's length times width, is shown in the figure. And then each little Ri, each little rectangle there, let X sub I, Y sub I, be the point that's closest to the origin. So if this is the little rectangle here, this point right here, X sub I, Y sub I, is the point on that rectangle that's closest to the origin. And so up here, when you're looking at a little patch of tangent plane, TI, that patch of tangent plane, if I blow it up, let's blow it up. Here it is. This is a patch of tangent plane blown up. We're going to find the area of this tangent plane patch, and it's a parallelogram. And I claim you guys know how to find areas of parallelograms. Yeah. Well, how are we going to do that? So this point here has coordinates X sub I, Y sub I, and the Z coordinate, since it's on the surface, is F, evaluated at X sub I, Y sub I, like that. That's that point closest to the surface of TI. This is our tangent plane. And I'm going to label that point A. And then how about this point over here? I'll label it B. And this point down here, I'll call him C. And this point over here, I'll call it D. Fine. So the surface area of the entire surface, which is going to be, we'll take the Riemann sum of all the little surface area patches, is going to be approximately equal to the sum of all the tiny areas of the tangent plane patches. Fine. And then we're going to get this little delta T sub I right here, this area. So this is the part that's a little tedious, but here's the good news. I want you to recall that if you have two vectors that are adjacent side lengths of a parallelogram, and this is something we learned like the first or second week of class, this area was the magnitude of the cross product of U and V. Do you guys recall this handy fact here?
Yes.
I hope so. It's going to be on the final.
Yep.
So what the heck does that have to do with this little delta T sub I we're working on here, trying to get the area? Well, here's my plan. I am actually going to find this vector here. I'll call this vector U, but it's also the vector AD. And then this vector over here, you could call it V, but it's also the vector AB. So I'm going to do that by using the knowledge we went over like the first week of class, terminal minus initial when you have points to create a vector. But let's put coordinates here. The coordinates for B, since it's kind of going in the positive y-axis direction, so the x coordinate is the same as A's, but the y coordinate is going to be y sub a little bit extra, yi plus 1. And then the z coordinate will simply be f evaluated at the x and y coordinates there, x sub I, y sub I plus 1. Now this point C, since he doesn't share the x or y coordinates of A because he's pushed forward in both directions, x sub I plus 1, y sub I plus 1, z coordinate is f evaluated at x sub I plus 1, y sub I plus 1. And then finally, this D point over here, his coordinates are, he shares the same Y coordinate as A, but his X is, because he's more in the positive X direction than A is, his X is X sub I plus 1, Y coordinate is Y sub I, Z coordinate is F evaluated at Xi plus 1, Y sub I. Fine. So now let's form the vectors. And this is good review, really good review. I claim. So if you can follow me on this derivation, it's good review for the final. Well, the final's so far away. Not really. It's 5.5 weeks away. Closer than you think. So here we go. The U, which is the vector AD, is going to be this big old vector. We're going to go terminal minus initial, terminal minus initial. Okay, AD. So you're going to go x sub I plus 1 minus x sub I, comma, y sub I minus y sub I. Hey, but that's 0 exactly. And then f evaluated at x sub I plus 1 y sub I minus f evaluated at x sub I y sub I. Fine. So now we're going to do some renaming, and then we'll get the other vector. Stay with me on this. Since the x sub I plus 1 minus x sub I is a difference of x coordinates, we're going to rename it delta x sub I. It's a change of x. And y sub I minus y sub I is a big fat 0. Fine. Now, this is the part that's really kind of interesting. We're going to do two things. We're going to replace this x sub I plus 1, this guy right here. We're going to replace it. Why? Well, if you use this formula here, that x sub I minus, or plus 1 rather, minus x sub I is equal to delta x sub I, and then solve that formula for x sub I plus 1, you'll get that x sub I plus 1 is the same as x sub I plus delta x sub I. And you're probably thinking, boy, this is really ridiculous. Why are we doing this? Because we're getting somewhere. Okay. And then, so I'm going to do that. And then I'm also going to multiply this last component of the vector by a special version of 1. You're like, oh, are you kidding me? No, I'm not kidding you. And the special version of 1, and this is the trick here, is going to be delta x sub I divided by delta x sub I. Ew, why? Ugh. Go, stay with me on it. Okay, so here I go. I'm replacing the x sub I plus 1 with x sub I plus delta x sub I, comma, y sub I minus f evaluated at x sub I, y sub I. Okay, now this special version of 1, the denominator, I'm just going to swing it underneath the difference there, and the numerator, I'll keep it outside like this. So this is what I have for that last component. Oh my goodness, you made it look worse, like 10 times worse. No, we didn't. Because what we're going to do now, if you're noticing what this quotient looks like, this is known as the difference quotient when you're doing derivatives. And if we take a limit of this difference quotient as delta x sub I goes to 0, that is going to turn into something. Does anybody recognize that?
Isn't that the limit?
Well, it's a limit. Yeah, we're going to take a limit right now. Limit delta x sub I goes to 0 of that. What does that look like to you? Does anybody remember? Maybe not. Do you remember when we studied partial derivatives?
Yeah.
Does everybody see that one of these difference quotients I have on the screen right now, which is a limit of a difference quotient,
Yeah,
what I'm looking at? Which
Yeah.
yeah,
one?
it kind of looks the same. It's similar.
Which one, fx or fy?
The FX.
Thank you. Really? Yeah, ooh, wrong one. Where the heck am I? Here I am. Nope, back to here. So what I'm saying is that limit there is looking very, very familiar, and it is familiar. It is the first partial of f with respect to x. Oh yeah, x sub I, y sub I. And then we're multiplying it by that numerator, x sub I. So there's the u vector. And so let's save that for later because we got him done. And then, of course, I run out of room because I never give myself enough room. What else is new? Let's go get the other vector. So what other vector are we talking about? I want to get this vector here, AB, because then I can take the cross product of u and v to get the and then get the magnitude of that and get the area of the parallelogram. So we're going to do terminal minus initial, and terminal minus initial to get the other vector. Here we go. So AB, take the difference of the x coordinates. Oh, x sub I minus x sub I, hey, that's 0. And then we're going to go y sub I plus 1 minus y sub I. And then we'll do f evaluated at x sub I, y sub I plus 1 minus f evaluated at x sub I, y sub I. Fine. Now we're going to do some of the cleanup. This is 0. This is going to be renamed delta y sub I. And then this y sub I plus 1, if you solve the equation that delta y sub I equals the difference of the y's, if you solve it for y sub I plus 1, you will get y sub I plus delta y sub I. And then once again, this last difference, I'm going to multiply it by a special version of 1, where the special version of 1 is going to be delta y sub I over delta y sub I. And so when I do that, and then also take a limit after I do a little bit of rewrite here, you'll recognize this as the other difference quotient for one of those partial derivatives there, like this. And then we'll multiply it by delta y sub I over here. And this guy right here is, you guessed it, the first partial of f with respect to y. So there, then we'll evaluate it at x sub I, y sub I. Okay, and then we still have that delta y sub I factor. Finally, okay. Now what? Well, now we're ready to do the cross product of u and v. Oh man, you thought cross products were going away. Nope, they're here. So we're going to go, all right, I hat, j hat, k hat, and then delta x sub I, 0, and then the first partial of x evaluated at x sub I, y sub I times delta x sub I, 0, delta y sub I, first partial of f with respect to y, x sub I, y sub I, delta y sub I. And then using that determinant format, I hat minus j hat plus k hat. You know this, you've seen it. I'm going to do a little bit of liberty with the notation just to make it a little bit cleaner. This is delta x sub I, fx, delta x sub I, 0, fy, delta y sub I. Here is going to be delta x sub I, 0, 0, delta y sub I. Okay, and then when you do the determinant methods here, this is going to be 0 minus the partial times delta x sub I, delta y sub I, times your I hat minus, and then this one is going to be the first partial with respect to y times delta x sub I, delta y sub I, j hat plus, and then the k hat is just going to have delta x sub I, delta y sub I for the factor in front of it. And if I rewrite this in component form, because quite frankly, that's my favorite, I want you to notice that all three of these components have a common factor. And I'm going to pull it out. These all have a minus here. I'm going to pull the common factor out in about 2 shakes here because I can. They all share it. Do you see a common factor between all three of these components?
Yes.
What is it?
Delta x of y, delta y. Sorry, x of y.
Yeah. So I'm going to pull that puppy outside and then keep everything else inside the vector notation here. And boom, there we have it. Okay. So folks, this big mess here, the vector multiplied by delta x sub I, delta y sub I, which you also can rename as delta a sub I over there, is what we call the surface area element. Yeah, surface area element. What the heck is that? Well, from now on till the rest of the semester, including the final, if you ever see D big S, that means they're asking you for a surface area element. So now we're ready to complete the total surface area. I'm almost done with this proof. So what we're saying is the total surface area, that was our original goal, I hope you didn't forget, is approximated by summing up all of the n tangent plane patches, delta t sub i's, but that is the sum of all of these, oh, I forgot. This is almost the surface area element. I forgot. I needed to take the magnitude. Sorry. Skipped a step there. So the magnitude of this is the square root of the sum of the squares of each and every one of these components, right? And when you square a negative, you guys know it goes positive. So I'm not going to bother putting the. So here's your surface area element, delta a sub I. So you're going to go, oh, and that's the area of the parallelogram. Okay. So you're like, oh, okay, I got this big mess here. Oh man, this is horrible. Really? Is it this bad? Yes. Sorry. And take limit as you tighten the partition. So as the norm of the partition goes to 0, or each of those little rectangles gets teenier and tinier, and then you're good. And then you'll get the surface area. Okay, so this proof took a long time, but now you have it. So I just thought I'd do that for you so you could see that the reason why I went through all of this work wasn't to waste your time. Okay, I want you to get why the surface area, I'm going to give you the official definition now, is what it is, why it's weird. Because I don't want you coming up to me, after class going, why? Why is it that whole yucky thing? Because of the fact that we were adding up a whole bunch of little bitty areas of parallelograms. And to find the area of a parallelogram, we had to get those adjacent side lengths of the parallelogram, which are vectors, take the cross product, take its magnitude, and then we have it. And it's wacky. It's like, it's ugly. I won't lie. Sorry. So now here's the official definition of surface area. So from now on, when anybody says, go find the surface area of this surface, F, and they're giving you that capping surface that they want to take the surface area of, the generic look is going to be a double integral. And instead of an R down there, you're going to see an S. That's right. You're going to see an S. And then instead of dA, you're going to see a ds. ds stands for surface area element. Do not confuse this with dA, which is plain old area element. Very different. Now, this is basically, I want to tell you a little secret. This is called a surface integral. It's a special double integral known as a surface integral. And we'll do more of those when we get to the vector calculus module of this course. We're going to do surface integrals like on steroids, but this is a baby one where the integrand is only a 1. And I say the integrand is a 1, but kind of not really, because this surface integral, like all surface integrals, is not integrable until you change it up. What do you mean? You need to rewrite it as a regular double integral where you're integrating over a region in the xy plane. So the projection of that surface onto the xy plane is going to give you the R, the region, and the surface area element is this awful looking radical, square root of 1 plus the first partial with respect to x getting squared, plus the first partial with respect to y getting squared, and then dA, the area element. Now, sometimes it's such an ugly radical that it might not even be integrable, because sometimes radicals can be pretty bad. But if it is, then you should be able to find a surface area. And that's pretty gross. Okay, so if you don't feel gobsmacked by now, you should be. Okay, fine. So what else? So the similarities that I want you to notice from all the calculus classes that you've taken. Calc 1. In Calc 1, you can actually use a single integral to find length on the x-axis. Yeah, that's right. Like here's the x-axis. Here's A, here's B. I hope you can appreciate that this length here is B minus A. But you can actually represent that with an integral. Yeah, that's right. You just do the integral going from A to B and you integrate a 1. Yep. Because you'll get length. And then in Calc 2, you learned how to find arc length on the xy plane. Well, what do you mean? Well, here's a little picture. You were given, say, a function y equals f of x, and they asked you, and you did some arc length here in this class also, so this is also Calc 3, finding the arc length of that curve. And so believe it or not, the arc length was the integral going from A to B of little ds. That's the arc length element. And the arc length element, and they didn't teach it to you like this, but that's what it is the square root of 1 plus f prime squared dx. Now, in Calc 3, we learn that area in the plane of some region here, you know, let's say you had some region like this, you can represent that area with a double integral where the integrand is a 1. So I want you to notice this is sort of analogous to the length. And now when we kick it up a notch and we find surface area in 3D, you're going to go, okay, big S is equal to double integral over S ds, but that is, when you change it to a regular integral, this yucky square root, I don't feel like rewriting it, but you just saw it up there in the definition, blah, 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 dA. So these all kind of are somewhat related. If you can see there's some connections between all of these, good for you. Let's do 2 examples, and then I'm going to move on to triple integrals. That's right. No rest for the weary. So let's see, 3. Do I want to do 3? I guess I could. All right, let's find the surface area for the portion of this plane that lies above a circle in the xy plane, and I'll draw the picture. You guys all know how to sketch a plane. I hope you do by now. So this plane would have x-intercept of 2, y-intercept of 2, and a z-intercept of 2. So you can sketch a portion of the plane. You're not being asked to find this surface area. Careful, that's not what they're asking. Well, they just said, No, because then you could just use your area of a triangle and skip any double integrals. So the portion of this plane that I just sketched that's hovering over the portion of the circle that is, I'm trying to change colors here. Come on, be cooperative. This the surface area, the portion of this plane that lies above the circle, and this is your circle here, but we only want to find how much of it lies above the circle in the first quadrant. So here's your circle of radius 1. So the portion of the plane that lies only above the circle is this right here. You're trying to find the surface area of that portion of the plane that's hovering above the circle. Kind of looks like a pizza slice. So the way you're going to do this problem, and it is a little bit tricky, and this is going to be similar to something I'll put on the quiz on Sunday. You got to know how to do surface area. What is your capping surface? Your capping surface, which we like to call f of xy, how do we find it? Well, you're going to solve the plane equation for z. And that's pretty easy because you're just going to subtract x and y from both sides, and you'll get 2 minus x minus y. There's the capping surface. So good news, you can now get your 2 partials, fx and fy, because you'll need those when you're putting together your surface area element. So this is going to be, ooh, easy, -1 and -1 respectively. So your surface area, which is denoted big S in mathematics, little s is arc length, big S is surface area. But for us, that's going to be the integral over that little quarter of a circle R, square root, big square root, 1 plus first partial of f with respect to x squared plus first partial with respect to y squared. But this is just a constant. Does that always happen? No, but when it does, you're lucky. And so I'm just going to pull that multiple out like this. Now, here's the part where I'll allow you to do shortcuts. Okay, listen up. This is the area of the region in the XY plane. So let me just remind you that that is a quarter of a circle centered at the origin of radius 1. Now, you could set up a double integral for that, and we could even do it in polar. It would be theta going from 0 to pi halves, r going from 0 to 1, and the area element for polar coordinates is r dr d theta, etc. But let's do a shortcut because we can. Remember that a double integral with a 1 for an integrand represents area. And so the area is, they just want the area of this quarter of a circle. So this surface area is square root of 3 times area of 1/4 of the circle. That's all. And so you just use your knowledge of area of circles, and you know pi r squared, but we want 1/4 of that. 1/4 times pi, the radius is 1. Oh, and we're almost done. And so the surface area is square root of 3 pi fourths square units. And we're done with that example. That's the surface area of the portion of the plane that lies directly above the quarter of a circle. Pretty easy. We didn't have to do anything hard. Let's do a couple harder problems, and then we'll do triple. Oh man, I'm just pushing it. Why are we taking so long? Oh, I know. So this one's harder. We're going to find the surface area of the portion of a paraboloid. So may I remind you, a paraboloid is a kind of like a 3D analog of a parabola. And this paraboloid opens upward with a vertex there at 0, 0, 1 on the z-axis. Nice. Now, do we want to find the area, the surface area of that entire paraboloid? No, that would be infinity. Don't be silly. We want to find the portion, surface area of the portion of the paraboloid that's like directly overhead. Like here's the region R, the unit circle here. This is your region R, the unit circle in the XY plane, centered at the origin there. So the portion of the paraboloid that's hovering above that circle, the surface area, I'll shade it in red, would be kind of looking like a cup. Okay, so that would be the surface area of the paraboloid we want to find. Fine. So you got to do some work. These always take a lot of work. And by the way, when I put these on a midterm and a final, they're always worth a lot of points. And students always think, she just is covering surface area. She's kidding. She doesn't mean it. You know, and then they don't really study surface area. And it's like, no, I was not kidding. Like, know how to do it. It's not that hard. Put it all together. Study it. So fx is 2x, because your z here is your f of xy. That's your capping surface. Your fy, your partial with respect to y, is 2y. Okay, fine. So your surface area, no, I don't want to go to File Explorer. Surface area is the double integral over the surface ds, but we rewrite it as a regular double integral with the square root of 1 plus fx getting squared plus fy getting squared dA. So for us, that's going to go boom, boom, 1 plus 2x getting squared plus 2y getting squared is your radicand, and then dA. Okay, now, this is pretty gross right now. Both of these terms here, since I have a 4x squared plus 4y squared, I'm going to factor out the 4 from the last two terms in the radicand. And then, believe it or not, I'm going to convert to polar, because this whole problem lends itself as the perfect polar candidate, unless you want to try to integrate that in rectangular coordinates, and I sure don't, okay? So the region R here, since it's a unit circle, R is blossoming from the pole, that's fancy polar world origin, out to 1, and theta is making an entire revolution, 0 to 2 pi. So those are going to be the limits. And by tradition, theta is the outermost integral. This radical is 1 plus 4r squared. The area element, be a pirate, r drd theta. And this is totally integrable using the power rule and u sub. And tell me what u is. It's 1 plus 4r squared. What is du? 8r dr. Good news. I already have an r and a dr in the integrand. I just need an 8. So I'll put one in, provided I multiply the front by its reciprocal. So now this integral looks like square root of u du, and you guys, little side work here, know that that's the same as u to the half, and the antiderivative is 2/3 u to the 3/2, and then so I'm going to pull the 2/3 out, and I'm going to have the 1 plus 4r squared to the 3/2, and I'm evaluating that between 0 and 1. I'm going pretty quick here, sorry. We reduce that to 1/12. So I'm going to have 1 plus 4 times 1 squared, that whole thing, to the 3/2, minus 1 plus 0 to the 3/2 d theta. This is going to be some funky number that's awful. 5 to the 3/2 minus 1. I'm going to just leave it like that. For those of you who are like, well, I don't like 5 to the 3/2. It bothers me. Fine. Then simplify it to 5 square root of 5. I don't care. It's all the same to me. I'm good. Okay, now what? Now you're just doing the last integral where there's only a 1 left in the radical, in the integrand rather. Well, that's easy. So you've got this weird number, 1/12, 5 to the 3/2 minus 1, and your integrate 1, that's just theta going from 0 to 2 pi. So you're going to get 1/12, 5 to the 3/2 minus 1 times 2 pi. Please reduce to lowest terms, otherwise I dock you a point. And it's going to be this 5 to the 3/2 minus 1. That whole mess all over 6 times pi. And this is a positive number, and it better be because you're doing surface area. So it's about 5.33 square units. And that's the surface area of the portion of a paraboloid. Yay! Questions?
Could you scroll up just a little bit above?
Sure. Tell me when. Is that
A
good?
little more.
A little bit more?
A little more. Yeah.
A little bit more.
Yeah, right there, right there.
Right there? Okay, you got it. No worries. Okay, so the point that I want you to get from this, is, a couple points, is surface area involves a surface integral with this surface area element that's got this nasty radical in it. And here it was integrable using the power rule. So know how to do your power rule. Come on, that's Calc 1 material. Graduates of Calc 1, you should be good. So let's do another one that involves the power rule. It's one of my personal favorites. By the way, this one I just showed you is a classic. Like every calculus textbook known to mankind has some flavor of this one I just did. It's so common. Know how to do it. And the original one I did too, of the portion of the plane. So this portion of the paraboloid, common. So the last one is, want to see the meme first? Oh, I love this. There's a polar bear and there's a Cartesian bear. I love that. Isn't that cute? You gotta love it. You guys have no sense of humor. It's sad.
Technically, we're all muted.
You're all muted, but you're laughing hysterically, right? Okay. So example 6 is, you're probably going to hate me because of the algebra involved, but I think I put this on like definitely one of my math labs, so check it out. We're going to find the surface area of the portion of a sphere, not the surface area of a sphere. There's already a formula for that. I think it's 4 pi r squared. A portion of the sphere that lies inside of a cylinder. Oh, so you know, you could do this in Geogebra, so I thought I would show you Geogebra. If you Google up Geogebra 3D calculator, it's kind of fun. Where'd it go? I thought it was there. Oh, there it is. You can graph some, fun things like, what if you just want to graph that sphere? Well, okay, let's go check it out. Oh, I'm totally blowing it. Sorry. I'm thinking it's like, okay, x squared. I got to jump out of being that. How do I get there? Maybe there I go. Plus y squared plus z squared. I'm just using the caret to do the squares. And that's equal to 25. So you guys should know that's a nice sphere centered at the origin, radius 5. We love that. And then we want a new input here. So what is the cylinder? And you guys remember cylindrical surfaces, right? It's just this x squared plus y squared equals, come on, baby, equals 9 is going to look like, and oh man, I need to change the color of that. Let's do settings. Color. Let's change him to blue. How about blue? How about green? No, green. Okay, well, whatever. Okay, all right. So the thing I need you to imagine here is you notice that the cap up here on the sphere, we want to find that surface area as well as the surface area down below, because that's also enclosed in this cylinder or this can. So we want both caps. We want to find the surface area of the North Pole and the South Pole. But good news, we have symmetry. In other words, in this sphere picture here, the North Pole surface area will be exactly the same as the surface area of the South Pole. So we're just going to set up the double integral representing the area of the North Pole, and we'll multiply by 2. Easier. Nice. Okay. That's the plan. So what I'm going to need to do is, oh, and then I said, let's use polar coordinates. Sorry, that's my other meme. So what is my z? What is my fxy? Because it doesn't seem like they gave it to me. They gave me the sphere, and we are finding the North Pole of the sphere surface area and the South Pole. So you're going to need to solve for z. Oh, man, really? Yeah. And so you'll square root, and don't forget your plus or minus. So which one do we use, the plus or the minus? Well, since we'll just use the North Pole only, we'll worry about the positive, and that just gives you the upper hemisphere of that sphere. So we'll do that. So I'm going to rewrite this using exponents because we got to go find the partial derivatives of this guy, because this is our f that we use in the definition. So fx, using the chain rule here, differentiating with respect to x. I know it's kind of gross. And I'm going to reduce this and also rewrite it with positive exponents and then put the radical back in. And fy is similar. I'm doing it over here. The partial with respect to y, chain rule again, chain rule, chain rule, chain rule. And when I rewrite this, I get that. So I got my first partials, and they're not very pretty. And it's like, oh man, this is not looking good. And it is going to be messy. Really? Oh, yeah, I'm not going to lie. So your surface area, which is the double integral over the surface, ds, will get changed to a regular double integral over the region. Now, what's the region R here? Like, oh, I don't know. Well, if you look at the picture here, the region in the xy plane is the region bounded by the can. The x squared plus y squared equals 9. So that's going to be the circle. Oops. The region R is the circle centered at the origin of radius 3. So the area, the surface area element, remember, is this big old radical dA. I know. It's getting bad, isn't it? Yeah, I know. Now what? Try integrating that. But I don't want to. But here's the good news. You're going to try to rewrite the entire radicand as a single quotient. Really? Yeah, and you can. And believe me, it's going to clean up real nicely. In other words, this 1, if you multiply the numerator and denominator of the 1 by the LCD, the 1 turns into x squared plus y squared over x squared plus y squared. And now, since all 3 terms have a common denominator, you can just sum up all of the numerators together. Watch what happens, people. This is beautiful. Did I screw up somewhere?
I was going to ask you if you were missing the.
Yeah, I'm totally screwing up. I'm sorry. I'm trying to go so fast. This should be square root of 25 minus x squared minus y squared. I knew there was something looking too pretty about that. Ooh, I apologize. Yeah. So this 1 needs to be, this is 25 minus, yeah, that's our denominator. So our 1 has to be 25 minus x squared minus y squared all over 25 minus x squared minus y squared. I know it's kind of a mess here. So now, what does that look like to you? This is supposed to be minuses. Minus. Well, does anything clean up, or does this still look like a terrible mess?
The numerator is 25.
Yeah, the numerator, you can add and subtract, you know, these terms, and they add to 0. So that looks a little nicer. But it still looks pretty bad. Like, how the heck would you integrate that in rectangular? Like, if you change dA right now to like dy dx, would you even want to try doing that? I don't. Yuck.
Convert it to polar.
Convert to polar. Absolutely convert to polar. And remember, the region R is this right here, and the R is just 0 to 3. Theta is doing its whole revolution, 0 to 2 pi. So you're like, okay, that looks fine there. And then square root, this can be rewritten as square root of 25 divided by square root of 25. And if I factor out a negative from the x squared and y squared terms, we can replace this with r squared, and this is just a 5. So I'm going to pull the 5 out. And then I'll have square root of 25 minus r squared in the denominator. The area element, be a pirate, for polar is r dr d theta. And now you can use your power rule. U is 25 minus r squared. Du is negative 2r dr. And you do have an r and dr in there, so you just need a factor of negative 2. So I'll divide out by negative 2. And then you hope this is all going to work out nice, right? Now, there's one thing I'm forgetting. Remember, I said I was going to do the North Pole and multiply by 2. So I probably should do that right from the beginning so that when I do get my final answer, I've got the surface area of the North Pole and the South Pole. Now, if they just ask me for the North Pole only, and they may do that on a homework, so be careful. I'm not just putting these 2's in willy-nilly. I'm doing it because my example, they want both caps. You may not have to do the double. Okay. Now, this negative 2 and this negative 2, oops, I need that negative 2. What am I doing? So this right here is looking like du over square root of u right now. So now what you're going to do is do your Calc 1 material. That's u to the negative half. You're trying to integrate. And remember, that's going to end up being 2, positive 2 u to the half. Okay. So this 2 and this 2 reduce out. So what do we have now with a little bit of cleanup? We've got minus 5. We have the outermost integral, which we'll eventually get to. And then this inner integral, which we finally got the antiderivative of. You've got that, and you're evaluating it between 0 and 3. And then eventually you'll do your d theta. Okay, nice. What a mess. Yeah. So this 2 I'm going to pull out. So you got negative 10 integral. And now be careful. The common student error that I see if you can find this error. Do you see it? I'll get students who do this. What's wrong? Play teacher. Play teacher, kids. What'd I do wrong?
Forgot the 1/2.
Yeah, I forgot the exponent. This is super common that students, when they're all doing their thing, and I know it's an honest mistake, and I always give partial credit, but my math lab won't. Like when I go in there and grade it, I have to turn a 0 into something other than a 0 to give you something. So you got to be careful. So what we have here is square root of 25 minus 9, but hey, that's square root of something nice. That's square root of 16. Minus square root of 25. Ooh, that looks pretty good. That doesn't always happen. 4 minus 5 is -1. Pull the -1 out in front, but -10 times -1 is +10. Ooh, this is turning out to be kind of nice. And when you integrate 1 with respect to theta, you'll just get theta. Final answer is 20 pi square units. Okay, not bad. So what turned out to be looking like kind of a messy, yucky problem ended up being not too bad. But we had to do a little bit of work because we had that 25 minus x squared minus y squared thing, and it was like not looking integrable at first. So, but it turned out to work out okay after we combined all the terms in the radical, and we got one single radical or quotient, and we were able to use the power rule. So that's another classic type surface area problem. And that's pretty much it. I've given you like the 3 biggies of surface area. It doesn't get any worse than that. Okay, so do a little bit of homework so you have a little bit of comfortable familiarity with it by the time the quiz 8 hits on Sunday. All right, and come to office hours. I have office hours today. You're always welcome. Come late, stay early, come early, stay late, whatever you want. Okay, we'll do problems. And there's a couple of you who are my regulars. You always come to office hours that well, maybe 3 of you I always see. Some of you never come. I don't know. Why not? Okay. So we're done with surface area. Let's get ready. Drum roll, triple integrals. Yay. So what's a triple integral good for? We just saw 4 things that double integrals are good for. What's a triple integral good for? A few things. So let's do a quick penumbra of a proof and get to it. Today, we're doing triple integrals in rectangular. On Monday, it's going to get a little bit challenging because we're going to switch it up to 2 brand new coordinate systems, cylindrical and spherical. There are coordinate systems in 3D that we're going to do Monday. Don't play hooky. Be there on Monday because those usually give people a little bit of a heart attack. All right, but rectangular, no big deal. You've seen that because we've been doing 3D and rectangular so far, and everything's great. So we're going to use a triple integral to do 2 things today: find volume and find mass. Fine. Quick derivation. You've got a surface here given by, maybe some function, whatever z of fxy, or 3 variables fx, y, z. But this is your Q. This is your solid region Q, which they better give you that. Which may be different from the F. I'm just telling you. So this may be given by, say, G of xy. Z equals G of xy. Fine. Then you partition that solid into a bunch of little itty bitty rectangular boxes, call it an inner partition. Take one little teeny tiny box, call it V sub I. Find the volume of that little delta V sub I, length, width, height, multiply them together. Little change of X, change of Y, change of Z. And since it's the ith little box, X sub I, Y sub I, Z sub I. Now, if you tighten up the partition so that the length of the longest diagonal shrinks down to 0, so this is where they're taking the limit, and you choose a point, a little arbitrary point in your box, you got a Riemann sum. And you're integrating this function of 3 variables over the solid. So when you take the limit as the norm approaches 0 of this Riemann sum, like this, it turns into a triple integral. Well, how come a triple integral? Because this delta V sub I, remember, was delta X sub I, delta Y sub I, delta Z sub I. So it's going to end up being a triple integral over the solid Q. and this delta V sub I turns into dV, provided the limit exists. Now, I want to say something about this. In the Briggs textbook, they may denote Q, that's the solid region that you're integrating over, as a different letter. They may use E, or they might use D. So I don't want you to think, oh, well, if you use a Q, then that's going to be different if somebody tells you to integrate over E or D or some other thing. No, it's just a dummy variable that they're using to call the solid that you're integrating over. That's all. So don't get freaked out. Now, this volume element, dV, for rectangular, the dV, has 6 possibilities, 6 of them. It's confusing. You could integrate in this order, dx, dy, dz. Or you could integrate dy, dx, dz. Or you could integrate dz, dx, dy. Or you could integrate dz, dy, dx. Or dx, dz, dy. Or dy, dz, dx. Wow, is that confusing? You got all these possibilities. Okay, well, for those of you that take probability, the probability theory is the first slot, you have 3 possibilities, and then after you choose one, the next slot has 2 left, and then you only have 1 left, but 3 times 2 times 1 is 6, and that's why there's 6 possibilities for order of integration. Now, which one of those is my personal favorite? My personal favorite is this one here. I prefer the dz to be the innermost integral, so I like to integrate with respect to z first, and then the dy dx. And you guys know dy dx is our personal favorite when we were integrating double integrals. So my second personal favorite, if I'm allowed to choose, would be this one here. This is my second favorite, where the z is still the innermost integral, but the x and y order was changed up. The other 4, I try to avoid at all possible costs. And I personally don't like having to switch the order of integration in 3D because it gets really confusing. So I'll just tell you that I'm going to do you a big personal favor, and I will not ask you to switch the order here in 3D. Now, I can't say that that's going to be true for other instructors of Calc 3, because I have seen other instructors' exams and quizzes, and I'll just tell you that they do. I'll just say you're welcome. So the my thing got cut off here for some reason, the evaluation of a triple integral. Let's see if I can find my Word document here. Why is that so terrible? No, it still looks pretty bad. What if I hit return a few times? So it's Fubini's, but on steroids. You're just going to extend it. So Fubini is going to help us out to iterate the triple integral. That just means put limits on it. So if you have your solid Q already defined up, where x goes from a pure number to a pure number, a to b, and y goes from a variable h1 of x to h2 of x, and z goes from some variable functions of 2 variables, g1xy to g2xy, and all of those are continuous on the region, and that would be the solid region. Then what you can do is you can iterate your generic triple integral given to you like this, and then stick limits on it. So, and the way they gave this one was the nice order of integration, but they might not. They might give it to you a little different, and so you may not have a choice but to do the different order. I just won't ask you to switch orders. Okay. Outermost integral is going from a constant to a constant. That's the rules. Middle integral has h1x to h2 of x. So remember that when you put the limits here, you don't want to have it be meaningless. It's okay to have variables here with x's because that's the outermost variable of integration, and we're iterating the middle integral. The innermost integral You can have all sorts of variables on, just so long as that variable doesn't match the variable of integration. Okay, so there's Fubini in action.
Can I ask one question?
Yeah.
Is this does this go into the theorem?
Yeah, that's part of the theorem.
Okay, I was just like it was clipped off, so I was.
Yeah, I know it got cut off on mine. That's Fubini helping you out. Put limits on there so that you can actually integrate. So what's a triple integral good for? Well, I can't tell you everything. That's why you're going to take the rest of the semester and stay in the class. But two applications that we can use a triple integral right now, right today, in the next 15 minutes. One of them is for volume of a solid. And if you're going to use a triple integral to represent volume of a solid, you're going to go triple, 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 and then the integrand will be a 1. That's how you know it's representing volume of your solid. Keep in mind with a triple integral, a big difference between triples and doubles is that you're integrating over a solid Q, a 3D thing, 3D creature, whereas double integrals, you're always integrating over a region that's two-dimensional, like in the plane. Big difference about what you're integrating over. Please keep that in mind, because if you don't, you probably will do pretty poorly on triple integrals because you're not getting it. Just saying. Because a lot of times some students do pretty good on double integrals, and then when we get into triple, they just lose it. I just don't get it. I'm sorry, don't get it. And I'm like, uh-oh. The other thing you can use a triple integral for is you can use it to find the mass of a solid, where your density function, and sometimes I use rho of x, y, z, but here they're using f, same thing. So you put that into your integrand, and then you integrate over the solid, and that'll give you the mass of the solid. So we already did mass earlier today, but that was mass of a planar lamina. That was a 2D item that we were finding mass of, but you can find mass of a solid also, given some variable density function. Fine. Now, how do you find the limits? Well, you know, I like to first figure out what the innermost limits are, like what's usually, which is usually z for me, if I have my choice. You know, what's z doing? You know, is z doing a floor to a ceiling or that kind of thing? So if you're looking at this picture here, notice that z has a floor here, this surface here, and then the ceiling is there. So your z, you know, when you iterate the innermost integral, you would put the floor and then the ceiling surface. Now, sometimes your floor is just the XY plane. If your floor is the XY plane, that is the equation z equals 0. So that would just mean you'd have a 0 down there for your lower limit for the z. Now, using your rules for iterating integrals, which one of the following is not a meaningful triple integral because it's violating one of the rules for putting limits on? Can you tell?
B. Would it be B?
Yeah, why? What's the baddie there?
On the dy integral, there's a z.
Yeah,
For the limit?
exactly. The innermost integral, there's a z there, not permitted. Well, why not? Because you already integrated with respect to z when you did the innermost integral, which means z isn't even allowed to be a limit after that point. Forget it. So that's not a meaningful triple integral. It's trash. This one is fine. This one's totally okay. This one's bad. Okay? So let's evaluate a meaningful triple integral. Let's do an easy one. It's not too hard. I just want you to get in the practice of seeing some triple integrals. And let's just try to do as many as I can here before we... Actually, I'm going to skip example 2. It's too easy. I'll give you the answer in case you want to do it on your own. Answer and come to office hours and try it out. And if you don't get 1/3 LN2, come see me and we'll talk about it together. Example 3, let's do something trickier. because this is similar to what I'll give you on the quiz. So set up and evaluate a triple integral representing the volume of a solid bounded by the plane x plus y plus 3z equals 12. And I'm gonna sketch the plane, and keep in mind, when they say 3 coordinate planes, that means first octave. They don't always tell you that, but that means this sort of the octave that's coming out of the page where x and y and z are all positive. So the capping surface is here, and then the walls of the solid are the 3 coordinate planes. So there's your solid region. And we did a problem like this when we did double integrals, because double integrals can be used to represent volumes also. So what's the difference between representing a volume in a triple integral versus a double? I'll show you soon. But first, let's do the triple. There's a generic. I like dz, dy, dx. That's my personal favorite order of integration for triple. Here, the floor of the solid is just in the xy plane. So the lowest z gets is 0. The highest z gets is the capping surface, but that means we're going to have to solve our capping surface for z. And when I do that, I get 1/3 times the quantity 12 minus x minus y. Okay. Now, what's y and x doing? Uh-oh. Well, you're going to look at the base of the solid again, because the base of the solid is going to give you access to how to iterate the last 2 integrals. There's your base. And then you're going to want to find the equation for that trace of the capping surface as it cuts through the xy plane. Keep in mind, that's when z equals 0. And if you set z equals to 0 in your plane equation, you get that. But that's just the equation y equals 12 minus x. So x is going from 0 to 12. If you put your little man in here, y is going from 0 to 12 minus x. And you're done setting up the triple integral representing volume. Okay, so if we start integrating this with respect to z first, because he's the innermost integral, the integral of 1 with respect to z is just z. Okay, sure. And then when you evaluate z at the limits, you get this. Now, folks, this is essentially the double integral representing the volume of the solid. Yes? You know where you put the capping surface in the integram? Hello?
Yes.
So what I need you to get, please listen, because I don't need, if you screw this up, I don't give partial credit really on these, because it's kind of hard to. When you're using a triple integral to represent volume, a 1 goes in the integrand, a 1. And then you iterate it, blah, blah, blah. And then eventually the capping surface does end up in the integrand as it would for a double integral, because a double integral representing volume, you put your capping surface there, okay? So, and they're equivalent, but follow directions, because sometimes I might say, you know, set up a triple integral to represent volume of a solid, and other times I might say use a double integral. Now, my math lab, if it's just having you type in the answer, it won't know the difference. You may have not followed the My Math Lab directions, and My Math Lab gives you full credit and full points. I won't. If I see on your paper that you set up a double integral to represent volume, and yes, you got the right answer, but you failed to set up the triple, oh boy, minus 50% at least, maybe more. Listen up, because I'm going to get harsh, because that means you're not following directions. Just getting the right answer is not going to be good enough for me. I'm just going to say et cetera here, because this is going to get kind of messy. And then the final integral is going to get so messy, you know, you might want to, well, hang on a second. Let me take that back. Let me go ahead and finish this up. I'll pull the 1/3 out. So you're going to get 12y minus xy minus y squared over 2. And you're going to evaluate this between 0 and 12 minus x. And it's like, oh God, are you kidding me? Ugh, this is awful. How bad is this? Oh, please kill me now. Ugh. But this one, I want to show you something. You could whip out your calculator and then type all this in. but sometimes you get lucky if you're good at factoring and recognizing like terms. So this is just an algebra problem I want you to notice. Do you notice the first two terms have a common factor of 12 minus x? And if you factor out the 12 minus x, do you notice that the other factor is 12 minus x, but this is 12 minus x, the quantity squared? But then the last term here is 12 minus x, the quantity squared, divided by 2. You can combine these into one term because they're both 12 minus x squared terms. So this is not as bad as it looks. And then you can just use u sub, okay? So I'll just let you figure that out. The final answer is 96 cubic units. Turns out to be a nice whole number. Does that always happen? No, but if it does, cool beans. So this next example, I like it for two reasons. One reason you can see right off the bat. The solid is being given to you in set notation, and be able to do this because some of you kind of screwed up the set notation problem that I put in last week's quiz. Oh yeah, I'm testing you on everything. And I know when you screw up. And some of you looked at it and you totally choked. When they give you set notation to represent your region of integration, in this case a solid, it's a blessing. It means you don't have to figure out too much because the guy that they're giving you as pure numbers is the outermost integral. So the outermost integral is going to be with respect to y. You don't have a choice there. The next thing you'll notice is if you have a single variable for a limit, that most likely is going to be your middle guy of integration. So that's going to be x is going from y to 1. And then the innermost integral is going to be your with respect to z, where the limits are 0 to xy. And they gave you the integrand here, okay, e to the z over y. Okay, so they gave us the information and we used it to set up the triple integral. And now let's integrate. How do you integrate e to the z over y with respect to z? You're going to use the exponential rule, where u is z over y, and then du, the derivative of z over y with respect to z, is 1 over y. So we need a factor of 1 over y in the integrand if we're going to keep going. So I'll put 1 in because y is considered constant with respect to z, so it's legit as long as we multiply the front of the integral by its reciprocal. Now this innermost integral is looking like e to the u du, which has the antiderivative e to the u. But for us, the u, when you back substitute, is y over z. And then you're going to evaluate e to the y over z between the limits. And I get z to the y over xy. Ooh, I know that's weird. Is that z over y? Sorry, I put y over z. This should be z over y. My bad. I'm thinking backwards here. This is z is xy over y. Okay, that's going to reduce. That's not too bad. And then e to the 0. Okay, that's going to be a 1. Oh, okay, fine. So what are we integrating now? You've got a y sitting out here, and then you've got e to the x after reducing minus 1, and then you have dx dy. Okay, that's not too bad because to integrate with respect to x, we're going to get what? The y is just a constant multiple. Keep it out in front, and you'll get e to the x minus x. And you're evaluating that between the limits, which are what, y to 1, I believe, y to 1, okay? And then you'll do the last integral last. And so this is going to look like y, and you'll go, okay, e to the 1 minus 1 minus e to the y minus y. Oh man, this is getting pretty gross. I know. And this is just a weird number, okay? That's just a weird number. E minus 1. So, and remember this y, you're going to have to distribute it. So you're going to have to do the integral of weird number times y minus y, e to the y, and then this is going to be a plus y squared. So you're integrating this with respect to y. So quickly, I'm just going to say that this term is going to need integration by parts, because y e to the y is going to need integration by parts. So I'll let you finish this up, but because this is just a single integral at this point, and you're graduates of Calc 1 and Calc 2. And the final answer is this wacky number, e minus 1/2 minus 2/3. I know, pretty weird. That's wacky, but it's the answer. And what I like about this problem is it's kind of a, it's a triple whammy. You have to do integration by parts and have to know how to do that. You have to kind of know that you're allowed to put in a variable if it's considered constant with respect to your variable of integration. So I love that part. That's a tricky thing. And knowing how to deal with set notation. All three of those in one problem. So the last problem, since I'm really running short on time here, I'll pick one. I'll just do example 5, and I think that's good enough. And I think after that, you can probably do homework and do okay on your rectangular. Rectangular is not that hard. They want us to set up a triple integral representing volume. And here's all the equations that are bounding the solid. So z equals 0 is just the xy plane. So we know the floor. And x equals 4 minus y squared. Well, if you graph that in 2D, it looks like that. It looks like a left opening horizontal parabola, and it's a cylindrical surface. So what does that mean? It means that it's going to look like that. You whoosh it in the direction of the missing variable. Oh, good God. And then z equals x is a plane that, oh boy, that's going to be, you know what, Geogebra might be a good idea right now. Screw it. This gets really tricky. So if I go, forget this, I'm going to go z equals x, graph it. And then this one, this one here, let's get x, what is it? X equals 4 minus y squared. Okay, let's hit it. Okay, so if you can imagine the solid that's bounded by that red plane and has wall, the floor is the XY plane and this green wall, if you will. If you could picture that, you're good to go. But you don't have to do the problem. but the base of the solid is kind of hard to figure out because it looks like the base might go on forever, but it doesn't, because in the XY plane, when you set z equal to 0, you get x equals 0. So the base of the solid is actually bounded right here. This is the base of your solid. This is kind of a hard problem. So your triple integral is going to look like this. dz, and I'm going to do dx dy because okay, yeah, 4 minus y squared. So 4 minus y squared, if you look here, did I graph 4 minus y squared wrong, people? I think I did. I said it was leftmost facing, and I graphed it rightmost. So it's supposed to be actually, sorry, I'm trying to go way too fast. It's supposed to be like this, leftmost facing, like this. Leftmost facing. You guys didn't even catch it. Oh, you're too tired. So z is going from 0 to x. X is going from what to what, and y is going from what to what to finish this out. And then I'll let you finish the problem. It's not that hard. So how do you do this? If y here, if you look at the intersections on the y-axis, you've got pure number to pure number. So you got to have your pure number outermost integral limits. Can't have variables there. And then what the heck is x doing? And since we chose the horizontally simple order of integration, you can put your little man in there. The little man is going to go lying down horizontally like this, like this. So his feet are the lower limit, and that looks like it's x equals 0, and his head is on this 4 minus y squared sideways parabola opening up to the left. And then you're done. You finally figured out how to set up the triple integral representing the volume. And I'll skip example 6 till next time, okay? This is not a hard integral to do, and if you do it, the answer should be, I get 256/15 cubic units. It's a weird fraction, but it is positive. So the hard part was figuring out the base of the solid because it looked like it might have been infinity base, but it's not, okay? Woo! All right. That's just crazy.